Okay, let's make a start then. So today I'm going to talk about some methods, and before I start on methods I thought I would just do a little bit of a classification of problem types, because we need to, before we can think about applying a method, we need to know what are the characteristics of the problem and what are we allowed to do. What operations are we allowed to carry out? That may, once we know the answer to that question, it may rule out certain methods and it may limit our choice of methods. So, I've classified problems into large scale and non-large scale, which I've called small stroke medium scale. So by small and medium scale, what I mean is that we are able to carry out a factorization of the matrix. So the problem is compute f of a. It might also be f of ab. So can we compute a factorization of the matrix? If so, then we can look at the separate cases of normal matrices and non-normal matrices. If a is normal and we can factorize a, then the problem is in a sense trivial, because we can just compute the whole eigendecomposition. If a is normal, the eigendecomposition will be q d q star with a diagonal d. So for normal A, the eigenvectors can be taken to be orthogonal. This is the key thing, or unitary. So this is for a normal matrix. And remember that normal means A star A is AA star. So that includes the symmetric matrices, skew-symmetric, Hermitian, skew-Hermitian, orthogonal, unitary, and other matrices, anything satisfying this equation. So for those we can simply compute the eigendecomposition, and then f of a will be just q f of d q star, which is essentially the Jordan canonical form definition, which just simplifies greatly in this case. Okay, so the normal matrix case, if you can compute an eigendecomposition, that's just about the best way to do it, to get f of a. So therefore it's not a very interesting case. The non-normal case is more interesting. So if A is non-normal, the best we can do in terms of transformations that are unitary is to get A to Schur form. So Q star T TQ. Where T is now triangular. So this is the Schur form. A unitary Q and an upper triangular T. And so now the problem reduces to computing f of t, which we've seen there are some explicit formulae for that. We saw that last time, but they're not very practically useful. So later in the lecture we'll talk about how to compute f of t in a good way. So the Schur-Parlett method will be the general purpose method for f of t. But there's also a whole class of matrix iterations that for some functions are appropriate. So here we have an iteration producing a sequence of matrices. Typically it starts with A, and you get a sequence x1, x2 and so on that hopefully converges to f of A. So these iterations tend to arise with functions that are solutions of algebraic equations. So square root, pth root, matrix sign function is another one that has some nice iterations for it. So for certain functions there are a wide variety of iterations like this, which are, well, both practically interesting and a lot of fun to analyze and to develop algorithms for. And there's all the usual questions about iterations arise. Do they converge? For what A do they converge? What's the rate of convergence? Do they preserve structure in the matrix? All kinds of questions come up when you have a matrix iteration. And in terms of implementation, the nice thing about these iterations is they only require matrix multiply and solution of multiple right-hand side systems. So just sort of basic linear algebra operations, so they're very easy to implement. In particular, easy to implement in parallel if you wished. And then the third class of methods are based on approximation. So these could be polynomial or rational approximations. Polynomial could be best on infinity, truncated Taylor series. Rational would be typically party approximation or some kind of best L-infinity approximation as well. And these will be tied to the particular function in question. In fact, these classes of approximations can be also applied to the large-scale problems as well. So they're quite versatile. So this would bring in the whole area of approximation theory to analyze the behavior of these approximations. Okay, so that's an outline of the sort of things we can do for the smaller problems, and we'll look at examples of those later. So once you get to large-scale problems, so A is large and sparse now. I'm assuming that we can't actually compute the full matrix f of A. So now the problem is f of A times a vector, and Marlies has talked about this already. So f of A times B, or another way of saying it, the action of f of A on the vector B. And I've picked out a couple of different cases here. First case is that we can still solve linear systems with A. So this means that we can do some kind of sparse, well, possibly we can do a sparse direct method. So sparse LU factorization with an appropriate choice of order of pivots to minimize fill-in. Okay, so assume a sparse direct method works for Ax equals B. And so this is sometimes called a backslash matrix, because in MATLAB, as you probably know, A backslash B is the notation for solving Ax is B. And in MATLAB, the backslash is quite intelligent, and if you give it a sparse A, it will just do a sparse LU factorization, and will give you the answer without you having to worry about the details. So this is a kind of, it's a matrix for which backslash in MATLAB would work, in other words, if A is stored in the sparse format. So if you have a backslash matrix, the sorts of things you can do, well, these Cauchy integral methods would be applicable. So remember, the Cauchy integral methods have got the requirement to evaluate the resolvent. So they had that term Zi minus A inverse. So this occurs inside the Cauchy integral. So when you apply a quadrature rule to the integral, you will have to evaluate this expression for lots of different Zj. And the Zj's are determined by the quadrature rule. So this is a sparse backslash. So that's one possible class of methods. And rational Krylov methods also, they require linear solves of the same kind of form. So, so both those methods would be applicable in that situation. So case 2 is you can only, so you can't necessarily solve linear systems directly, but you can compute matrix vector products. So A is so large and sparse that all we can do is A times a vector. That's the only operation we're allowed to do. You may have some more information about A, such as a bound for the eigenvalues, an interval on which, say in the case of asymmetric, the eigenvalues lie, and you might want to exploit that information. So Krylov methods obviously are applicable here. All they need is A times a vector. You can still use polynomial approximations because to apply a polynomial to a vector just requires applying A to a vector repeatedly. And I'll put others question mark. You might be able to think of other possible approaches here. So certainly the exponential integrators for very large problems would be in this case 2, where all you can do is multiply by the matrix A. Okay. So let's just keep those in mind, that classification as we go along, as to what actually are the range of available methods for a given problem. Another question that would come up, yesterday we were talking about estimating the condition number, and for that we needed a transpose or a star times a vector. So if we want to estimate the condition number by the power method I finished off with yesterday, we also need a star times a vector. So that would be, I guess, in a sense, another case or another question. Even if we can compute a times x, can we compute a star times x? Well, not necessarily. Just because you can multiply by a doesn't mean you can multiply by a star. Because a may be available only as some kind of operator rather than an explicit matrix. So that will be another refinement of this classification of can we do a transpose times a vector. But in looking at all these different approaches, you also have to think about the precision that you want. This is a pretty important aspect. Do you want to get full machine precision? So in IEEE double, which is about 16 decimal digits of accuracy, do you want to try and get 16 digits of accuracy? Is that your target accuracy for the computation? Often in solving PDEs and ODEs, well, usually the precision target is less than that because of the discretization errors in the differential equation are already much larger. So you could argue there's no point trying to solve the f of a problem to 16 digits if the discretization errors are already 10 to the minus 4. So a given method has to take into account the precision, and the method may have as a parameter the precision that you require. In many cases it won't, and it will just give you double precision. So for example, if you're using a sparse backslash methods just work in IEEE double, and they're trying to give you 16 digits, whatever there's no choice, they will work to 16 digits. And it's the conditioning of A that will determine the accuracy. But other methods, like iterative methods, will have a parameter, a convergence tolerance, where you can match the tolerance to the underlying discretization errors. And in the example we had yesterday about the healthcare problem, there'll just be a fixed tolerance that comes from the accuracy of the data that you've got. So this is another very important aspect, is what is the required accuracy? And that can completely change which is the best method for the problem. So there might be a method that works well with a tolerance of 10 to the minus 4, but if you put tolerance 10 to the minus 16, it might even fail to converge. So we need to keep those aspects in mind as well. Okay, so let's now look at some methods. And I just want to go back with a few historical comments about MATLAB. So this was the very first version of MATLAB, which Kleemoller demonstrated at the Householder meeting in 1984. This version of MATLAB was written in Fortran. It was not a commercial product. It was just something Cleve wrote for his students to use, to give them easy access to LIMPAC and IcePack, which were the old equivalents of LAPAC. And there are about 80 functions built in. Many of the names we still recognize, others have disappeared. I notice because this was written in Fortran, I think that you had a limit on the number of variables in a function name. In fact, they're all at most 5 letters, aren't they? So retu, just notice this retu there, that's probably just short for return. But what I want to point out there was a fun in the very first version of MATLAB, a routine called fun for matrix functions, along with all the usual suspects like SVD and LU and QR and so on. So fun was there right from the start, and here's the help for fun. It says for matrix arguments, the functions sine, cos, arctan, square root, log, exponent, power are computed with the eigendecomposition. So if Vd is eigx, then f of x is V Fd times V inverse. So this is using the eigendecomposition to compute matrix functions. So essentially it's using the Jordan form. And it says, the method may give inaccurate results if these badly conditioned. So Cleve is pointing out that, you know, if the eigenvector matrix is ill conditioned, this is probably a bad idea. And some idea of the accuracy can be obtained by comparing x to the power 1 with x. Yeah, well, that's just really again saying, what would x to the power 1 be? So with his way of doing it, what does it mean, x to the power 1? So he's computing x, no, it's x, isn't it? Notation. X is v dv inverse. So x to the power 1, he's going to compute as v times d to the 1 times v inverse. So x to the power 1, it just means you multiply the factors together, back together. So you've computed v and d by the eigen function, and then you just multiply them together and see how it compares with the original matrix. So he's really just computing the residual of the eigen decomposition. And if that residual is big, that's an indication that v is ill-conditioned. So I agree with that. So fun was there right from the start, and in an interview, Cleve said that the availability of this function in early versions of MATLAB quite possibly contributed to the system's technical and commercial success. Well, MATLAB's success is probably due to control engineers. They are why it became a commercial product in the 1980s. Because when Cleve taught a course on MATLAB at Stanford University in 1983-4-ish, there were some engineers in the audience, and they found this extremely useful for solving the sorts of control problems they had. And it was an engineer called Jack Little who then suggested to Cleve that they form a company and commercialize MATLAB. And control engineers, one of the things they need to do is solve algebraic Riccati equations. And Riccati equations can be solved with a matrix sine function. So I'm going to talk about the sine function later. Peter Benner next week will talk about Riccati equations. So I think if it hadn't been for those Riccati equations and the control engineers, we might not have MATLAB today. They are the people that recognized how useful MATLAB can be for solving these problems. So they were probably using fun with cases like the sine function. Okay, so MATLAB's always had matrix functions in it. Let's look at a few different types of, first of all, approximation methods. So remember, the exponential was defined way back by Laguerre and Peano via its Taylor series. So in a sense, you could say the Taylor series evaluation of the matrix function is one of the oldest methods around. I've written down the cosine series here. And there's a theorem that says that if you have a given radius of convergence for a Taylor series, in the scalar case, that the matrix Taylor series will converge provided the eigenvalues of the matrix lie in the radius of convergence. So when you have an infinite radius of convergence, as for the cosine, then this series works for any A. So we can think about just summing the series until the terms are so small that we don't need to add any more on. Just stop as soon as maybe the next term is bounded by some tolerance. Okay. Of course, there are bounds for the error in a truncated Taylor series in the scalar case, and there are some corresponding bounds in the matrix case. So we do have rigorous estimates for the error you make when you truncate a Taylor series. But what I've just said is really all thinking about exact arithmetic. In floating point arithmetic, there are other considerations to do with numerical cancellation. And these are well illustrated in the classic paper by George Forsyth called Pitfalls in Numerical Computation. So this was an American Math Monthly in 1970, and it's well worth a read if you've never looked at this paper. But there's lots of examples of what can go wrong in numerical computation in that paper. So he took the standard Taylor series in the scalar case, e to the x here, and he tried it with x's minus 5.5, working in base 10 with 5 digits of accuracy. And what he's shown here are the terms in the series. So we've got the 1, this is the x, this is the x squared over 2, x cubed over 6. and so on, and you can see that the numbers are growing before they start to eventually decrease. The terms have to decrease because it's a convergent series, but before they decrease, there's no a priori bound on what can happen, so the numbers can get very big before they get small again. So in this case, because of the cancellation, we get a very inaccurate result. I seem to have lost, I see I've lost the sum off the bottom of my slide. Aha, right. So we're going to have a look what the answer is. It's because I'm using a different beamer style here, that's why. Okay, so let's see, Forsyth. It's a graphic inclusion, right. All right. I'm not going to bother chasing up what the answer should be, but I know that he had hardly any significant figures in the answer. A slightly different case is if we take x is minus 9.9, you get a relative error. So if you do this in double precision IEEE double, and you take x is minus 9.9, you get an error of about 10 to the minus 10. So you lose 6 significant figures for x is minus 9.9, even in IEEE double. So here, with only 5 decimal places, I think he loses almost all the digits. Okay. So the point is that for a large x, the series will grow before it decays, and essentially the error is proportional to the precision times the largest term in the series. So the bigger that largest intermediate term is, the worse things are. So what we want to avoid is having series where we get this growth picture. So if you plot the terms in the series, so the kth term in the series, what you don't want to see is something like that with a big hump. What you would rather see is some kind of gradual decay. But this is going to cause rounding problems because the overall error will be proportional to the round off unit times that peak. Okay. So if we want to use this series, we just need to do something to make sure that x is not too big. That's the conclusion. And we'll come back to that later. So Taylor series are very widely used, very popular. A bit less well known, but more powerful, are Pardee approximants. So this is a beautiful bit of approximation theory here. So Henri Pardee came up with this idea in his PhD thesis in Paris. And really all a Pardee approximant is, well, the way I would think of it, it's just a rational function that reproduces as much as possible of a Taylor series. So we're expanding about the origin. So think of x as being, x is a small number here. So it's a rational approximation. PKM has got degree k, QKM has got degree m. So it's a degree k polynomial over a degree m polynomial. And those polynomials are chosen so that if you expand the difference between f and the rational, you get as high a power of x as possible in what's left. So what is that power of x? Well, you just have to look at a simple-minded approach, just look at the number of free coefficients. So PKM has degree k, so it's got k plus 1 free parameters. QKM has degree m, so it's got m plus 1 parameters. And so the total is k plus m plus 2 free parameters. But because we're dividing p by q, we lose 1 degree of freedom. So we can, we can always multiply P and Q by any number without changing R. So we've really only got K plus M plus 1 free parameters. And so we can use these free parameters, hopefully, to knock out the constant term, the x squared term, up to the xk plus m term. And so the first term that's left over would be x to the k plus m plus 1. Okay, so if you just think of writing down these conditions, you're going to get k plus m plus 1 equations and k plus m plus 1 unknowns, and if you can solve those, you will achieve that accuracy stated there, that big O, x to the k plus m plus 1. So that's just a simple-minded argument as to well, the best we can do. The theory of party approximants goes much more deeply into when and whether you can do this, because you can't always achieve that order of accuracy. It depends on the function and in general on k and m. But what Pardee did in his thesis was to show that for the exponential, this always works. For any k and m, you can achieve that accuracy. And he even gave explicit formulae for pkm and qkm in terms of binomial coefficients. So the reason we're interested in Pardee approximants is that if you look at the efficiency of achieving a given order of approximation, they're generally more efficient. So to get this order of accuracy, you would of course have to go up to the x to the k plus m in your Taylor series. And if you compare the cost of computing that with the cost of computing R, and with a matrix argument, the Pardee approximate will usually be the more efficient way of doing it. But what makes this all interesting is that there's no unique way to evaluate R. R is a rational function, and there's lots of ways of evaluating rational functions. So you can just evaluate it in the obvious way. In other words, you work out pkm of x, work out qkm of x, and divide them. Even there's more than one way of doing it. How do you evaluate a polynomial? You can do it by Horner's rule, but there are other ways, and because we need to get p and q together, Horner's rule may not be the most efficient way of getting both of them. There are continued fractions for representations of rational functions. I think we'll see one later. And partial fraction representations. So particularly in the matrix case, these can have quite widely varying costs and quite widely varying accuracy. So there's a lot of interesting questions about how to evaluate a Pardee approximant in the best possible way. So we'll see an example of this later, I think, for the matrix exponential. And in many cases of standard functions, there are explicitly known continued fractions and partial fractions. And I have to mention, because this is one of Gene Golub's favorite topics that he talked about many times, there's an intimate connection between Gaussian quadrature, Pardee approximation, and matrix moment problems. So in this arena here, there's some very deep connections between Gaussian quadrature, the Lanczos algorithm, continued fractions, and his book with Meron, called Matrices, Moments, and Quadrature, goes quite deeply into those connections. So those were approximation techniques. Let's return to transformation techniques. What I'm describing here is exactly what MATLAB does. Well, MATLAB did, sorry, in the very first version of MATLAB that I just showed a moment ago. So it's computing the eigendecomposition. So it has B diagonal, and then it just uses the formula at the top there. But we don't have to take B diagonal, so we can consider other possible choices of B. So if you do this, use this approach, then you have to be prepared to accept errors proportional to kappa x. So if we go for x is, A is x, B x inverse, well, so f of A is x, f of B x inverse. Even if you compute f of B, so let's call f hat the computed f. Even if the only error you make in this whole computation is just a single rounding error in storing each element of f of B, so you get a single error matrix here, which is of the order of the unit round off. I use little u for the unit round off, which is about 10 to the minus 16 in IEEE double. It's actually equal to 2 to the minus 53 in IEEE double. So little u denotes the unit round off. So even if you just make one error when you round each element of f of b, that one error, represented by delta b, that gives rise to this term here. So let's think of this as f of a plus delta f. Then delta f, the best bound we can derive for delta f would be norm x inverse times norm delta b, which is, well, the first part is kappa x, and delta b we're saying is about u norm b. So we're going to get a kappa x in the error bound, which is what I've said here. So if x is ill-conditioned, the matrix condition number norm x inverse, if that's big, then even if we just make one error, one single rounding error in storing the f of b part, we still have to expect overall errors proportional to kappa x. So we really want to keep kappa x small. We don't want to have an ill-conditioned matrix x. So that's why we prefer unitary x. And unitary matrices, of course, have perfect condition number. They have condition number 1 in the 2 norm. So if we then restrict to unitary x, then as we were saying at the start of the lecture, in the normal case we can get b diagonal. In the general case, the best we can do is b triangular. So I would generally stick to unitary x for stability reasons. I've got an example here done in MATLAB. So what I've done is coded up my own little version of the original MATLAB fun-m, and it just computes the eigendecomposition. Vd is Ig, and it applies f to the diagonal entries of d, and then transforms back. And I've tried this on the matrix 3 minus 1, 1, 1. I've used it to compute the square root of that matrix. So we get this as the answer, and if we check the residual, a minus x squared, we get an answer of order 10 to the minus 10. The condition number of v is about 10 to the 8 here. So we haven't quite lost 8 digits, we lost about 6 digits, but it's clearly proportional to the condition number of v. If you compare that with what happens if you call MATLAB square root m, so this is the built-in MATLAB function for square roots, and we'll see in a moment how that works. So it computes a residual of order 10 to the minus 16. So this does much better than this approach. So we really have lost, well, yeah, 7 or 8 digits actually there. And that's because of this ill-conditioning of the matrix, of the eigenvector matrix. So that really does bite you if you have an ill-conditioned similarity transformation. Now there is an intermediate approach, somewhere between using the shear form and between completely diagonalizing the matrix, which has been proposed over the years. So block diagonalization. So the idea is to try and compute a block diagonal form of the matrix. Probably the best way to think of it is that it first of all, and this is the way that the methods that have been proposed actually work, you first of all compute a shear decomposition, and then you do some more work on the factor t So you now compute your D as some further transformations, xt, x inverse, so that this is block diagonal. Okay, so you first of all compute the shear form, then you do some more work on T, and now it's non-unitary transformations that you're using, but you try and make sure that kappa x is below some tolerance, tol. So you choose some tolerance. You might say, I don't want to have kappa x bigger than 10 to the 3, and you force your choice of x's to satisfy that bound. Now the effect of the bound is that it will determine how big these blocks are. So if you take, if you were just to, well, if you put tol as infinity, you would just get a diagonal matrix, of course. Okay. So tol is infinity will just give you back the diagonal form. But if you say take tol is, I don't know, 10 to the minus 8 or 10 to the 8, you're now liable to get bigger blocks, much bigger blocks. You know, so you might get, well, you'll just get some size blocks along the diagonal. So the smaller the tol is, the bigger the blocks you will get, and ultimately you'll just get one big block. And what you want is to have lots of small blocks, otherwise there's not much point to doing this. Because when you have a small block, it's going to be easier to evaluate f on the diagonal blocks. So there's a compromise with this tol between maintaining accuracy and getting small diagonal blocks. The interesting thing about this calculation is that it involves solving Sylvester equations. So I won't go into that, but there's some nice algebra to see how you can actually block diagonalize. The main problem with this method, I would say, is that once you've got your block diagonal form, and these blocks actually are triangular, so each of these blocks is actually a triangular matrix, it turns out. But these triangular blocks themselves have got no special structure. So you've still got the problem of f of a diagonal block, and that's still a non-trivial problem. It may be a lot smaller, the problem, smaller dimension, but it's still a non-trivial problem. And there's no easy way to, you would then have to apply some other method to get f of the diagonal block. So I think that's why this class of methods hasn't really caught on. Although it's certainly an interesting idea. It's also difficult to know how to choose tol. So let's go back to the shear form and look at what is the standard method, or the basis of the standard method for evaluating f of a triangular matrix. So this is the Parlett recurrence. So Beresford Parlett at Berkeley in the early 70s noticed that if you write down the equation that expresses the commutativity of f of t and t, then if you look at the equations in that system, so ft is tf, this is, well, t is upper triangular, so f is also upper triangular. So this is n times n plus 1 over 2 equations in the same number of unknowns. Except that we know that fii is f of tii. Okay, we already know that the diagonal is just given by f of the diagonal of t. So we've got n plus 1 over 2 equations in, the number of unknowns is just given by the upper triangular part of f. So there's nn minus 1 over 2. Although if you look at the diagonal equations, they're just going to say fii times tii is tii times fii. So actually, there's really n less equations there. So we have the same number of equations as unknowns, and in principle we should be able to solve those equations. So Parlett observed that if you compute things in the right order, you can indeed solve these equations. And the right order, if you take the 3 by 3 case, so if this is our f, and remember we know the diagonal, so we already know these numbers. You can either compute f a column at a time or a superdiagonal at a time. So one way to compute f is this number, then this one, then this one. So going down the columns, or you can just go down the diagonals one at a time in that direction. That's the formula that you get when you solve these equations, and so the ordering will determine the indices of the I and the j. So we saw yesterday the formula when n is 2, that the 1, 2 element. So remember f12 is t12 times the divided difference of f t11 and t22. And you can see the divided difference appearing here. So for the 1, 2 element, so for the 1, 2 element, this summation is empty, and indeed this is just f11 minus f22, t11 minus t22. That's the divided difference there. So we can see the 1, 2 case coming out as a special case there. Okay, so that's the formula, just a simple finite recurrence to get all the elements of f. But of course, it only works if the tii and tjj's are distinct, because otherwise we're going to have a division by 0 in this formula. So that's an immediate problem with the recurrence. Now, you might think that's something we can surmount, that problem, because see here we've already expressed the 1, 2 element as a divided difference. And we know from that general theorem that every element of f can be expressed in terms of divided differences. So it might appear that the answer is, when we have a division by 0 down here, there should be some kind of divided difference formula that we can use instead. Or maybe we can just go to that theorem that had that big sum with the divided differences and use that instead of this recurrence. Well, that approach doesn't really work. It's just too difficult to code and too difficult to decide, again, when elements are closed and so on. So there isn't really any easy way to fix this recurrence to handle the case of repeated diagonal elements. This method, this recurrence, was used in MATLAB up until about 2002. So FunM in MATLAB just implemented that recurrence. So it could fail completely if you gave it a matrix with repeated eigenvalues. It would give a warning message, but it would give a very poor answer. So I'll say in a moment what replaced that. So this fails when t has repeated eigenvalues. So I can't really recommend the basic recurrence unless you are sure that you have nicely separated eigenvalues. But let's just take a detour for a moment to think about a slightly different problem, or a more special problem, which is the pth root problem. And in particular the square root problem, so x squared is a. If you have a shared decomposition of a, then a to the half is q t to the half q star. So the principal square root, and if we call, what have I called it here? So if we call u t to the half, then u squared, of course, is t. And we can try and solve this equation for u, because we know that uii is going to be tii to the half. T is upper triangular, u is also upper triangular. So from the diagonal entries of that equation, we get uii is ti to the half. Let's just look at the 2 by 2 case and just see what we get for the 1, 2 element. So the 1, 2 element of this equation is U11 T12 plus U12. No, sorry, I want to square U, don't I? So I'm just going to square U. So the 1, 2 element is U11 squared plus U12 times U22. And I want that to equal T12. So we're trying to solve U squared is T, and we're just multiplying out, and I've got that wrong as well. That's U11 times U12. So U12 is T12 over U11 plus U22. If I solve that for U12, which is T12 over T11 to the half plus T22 to the half. So I can just write down U squared is T and solve for the 1, 2 element. So I'll come back to that in a moment, that formula. But just in the same way as with the Pilot recurrence, I can carry on computing U either a diagonal at a time or a column at a time. It's just the same principle, but it's just a slightly different equation that we're solving now. So the formulae are up there. It looks rather similar to the Pilot recurrence. But notice now that this can never fail, because UII and UJJ are the principal square roots of TII and TJJ. They line the right half plane. So the principal square roots line the right half plane. So when you add 2 of them together, you can never get 0. So that denominator is never 0. This cannot break down. I'm assuming here that A is not singular. If you have 0 eigenvalues, then this could break down. But if you have 0 eigenvalues, you can't even be sure the matrix has a square root. So that we would normally rule that case out. So that was by Bjork and Habling. And if you look at their original paper, here's what they say. They say we started out trying to develop a method for the square root of a triangular matrix. They said we tried Newton's method. If in doubt, you want to solve an equation, always try Newton's method. And it converged remarkably quickly. It kept converging in just a handful of iterations. And that led them to think, well, if it's converging so quickly, there's something going on here. Let's look more carefully at what's happening. And they realized that there's actually a finite recurrence for computing U. So they didn't think of that directly. They first of all thought, let's apply Newton to U squared minus T is naught. And that led them to this recurrence. That's square roots. You can do a similar thing with pth roots. You just replace the 2. U squared is T becomes U to the P is T. And the recurrences get much more complicated, but they're still finite. And my former PhD student, Matthew Smith, worked out all the details. So the same sort of idea will work for any P, cube roots, 4th roots, 5th roots, and so on. So this is actually a very good approach. Because we're working with a shear decomposition, we've got perfect numerical stability. The cost is reasonable. For very large values of P, there are alternative methods that have a... So this method has a cost proportional to P. It's of order Pn cubed. There are methods that will get the P down to log P. So if you're worried about very large values of P, there might be alternative approaches that are preferable. But for small P, this is fine. And you can even generalize all this to the real shear decomposition, everything on this slide. So the real shear decomposition, as you may know, differs from the complex one in that the shear factor is quasi-triangular. So if A is real now, we now have A is QR Q transpose, and R is block triangular. But each RII is either 1 by 1 or 2 by 2. And R is real as well. So everything here is real. Q is real, A is real to start with, and R is real. So what this means is that the complex conjugate eigenvalues appear in 2 by 2 blocks on the diagonal of R. So that's where the complex eigenvalues go. If there are no complex eigenvalues, then R is just actually upper triangular. And so this approach will generalize very nicely to the real Schur case. You just now have to solve some equations with 2 by 2 blocks. So that means you can compute entirely in real arithmetic. The reason that's important is that, well, real arithmetic compared with complex arithmetic is more efficient, because to multiply 2 complex numbers, you basically need 4 real multiplications. So complex arithmetic in practice is quite a bit more expensive than real. So if we can keep things real, we generally prefer to do so. The other reason for preferring real arithmetic is that if you compute the square root of a real matrix via the complex Schur form, so your t in the Schur form is generally complex now, even though the answer is real, you will get some residual rounding errors that are complex. So the result you compute will likely have some small non-zero imaginary part. Which is a question?
Excuse me. In this case, the R would not be necessarily n by n, yeah? So
the whole matrix R, yeah, would be n by n, but the number of blocks, everything's n by n here, but the number of blocks will vary. So that I've just said k blocks. K will be anything from 1 to n. Well, no, it can't be 1. There could be about n over 2 blocks, or there could be just n blocks.
the sum of the size would
But
be n.
the sum of the sizes is n, yeah, that's right, yeah. But if you work with the complex Schur form, you will get probably some small tiny imaginary parts order round off in the result. What the MATLAB functions do is just set those to 0. But it's a bit annoying to have to get those small imaginary rounding errors. Just returning to the Parlet and the Bjork-Hamelling. So if you compare what happens in the case of the 1-2 element here. So down here we got this formula from the Bjork-Hamelling method for the 1-2 element of the square root of a triangular matrix. T12, I'll call it A up here. A is the same as T now. So it's T12 over root T11 plus root T22. That's what Bjork and Hamelling computes. But this is what Parlet computes. It's A12 times the divided difference for the given function f. Now, of course, those two expressions are equivalent, but the Bjork and Hamelling one is a little bit less expensive to compute. So it's actually a better expression. Moreover, the Bjork-Hamelling one doesn't have any problems when A11 and A22 are close. So there's some possible cancellation here, which cannot happen here. So it's interesting that the Bjork-Hamelling gives you a much better formula for the 1-2 element. But of course, it is exploiting the particular properties of f. So the problem with the Parlet method, in a way, is that because it's designed for general f, it can't really take advantage of the sort of cancellation that, if we were looking at this, we would just naturally rewrite this in that form there. But it can't do that. So I think that's actually a good time to pause. Right. So I want to go back to the application section, because there's one part we haven't done yet, which is the part that relates to Marlise's lectures. And for this, I just want to introduce these functions called the phi functions, which are related to the exponential. So the first phi function, phi 0, is e to the z. And the next one is e to the z minus 1 over z. And what you keep doing as you generate these phi's is you keep taking off more and more terms of the Taylor series and then normalizing so that the leading term is a constant. So the general recurrence is this one here, and an explicit formula for the phi's is given by that expression in yellow. So it's an exponential-like function You can think of it that all you've done is change the factorial in the denominator from j factorial to j plus k factorial. That's a family of functions. So where do these come up? Well, they can be helpful in solving differential equations. So as we all know, the y dashes ay linear constant coefficient equation can be solved in terms of the exponential. But what if you add on a constant term to the right hand side, a vector b, and if you have y naught is naught, you can show that the solution is now given in terms of phi 1. So it's t times phi 1 of ta times b. So an explicit formula involving phi 1. If you had a ct on the right hand side, so a linear time dependent term, it's now phi 2 that appears in an explicit formula for the solution. So the solution is t squared phi 2 of ta times c. And this carries on in the same way. So you can build up an arbitrary polynomial in t to be added to ay and still have an explicit solution to the equation, and that solution will involve all the different phi functions up to a certain degree. Okay. So the connection with exponential integrators is that you can use these that idea to come up with integration formulae. So I guess my simple-minded explanation of all this, as opposed to Marlise's detailed explanation, would be that I've got a differential equation that I'm going to write as the linear part ly plus whatever's left over. So ny will be the nonlinear part of the equation, and this is presumably come from some semi-discretized partial differential equation, so that L is some well-known operator. And if I take a really simple-minded approach, I can just say, well, I don't know what to do with the ny, so I'm just going to freeze it. I'm just going to approximate it by a constant. So replace n of yt by n of y0. So replace n of yt by this constant. So I now have y dash is ly plus a constant, and then I can use one of the formulas from the previous slide, or the second one, and I can write down that this is approximately now equal to this. So approximately because of this approximation, but this is actually the exact solution of my approximated equation. And that's basically gives rise to the exponential Euler method, one of the simplest of these types of integrator. So to implement this Euler method, you've got to do exponential of a matrix times a vector and phi function of a matrix times a vector. And Marley's talked in more detail about the history of these methods recently. The earliest paper I've looked at is the Lawson one, but as she said, there are other earlier papers on this topic. So I just want to say a word about the implementation. So this is just a slightly more complicated version of what was on the previous slide. So we've got our linear part AU plus our nonlinear part G, and I'm just taking the idea here of expanding in a Taylor series. So the nonlinear part I'm going to expand in a Taylor series. So I'm assuming I can compute these derivatives. How to get those derivatives is another question that is covered in Marlise's talk, essentially, Runge-Kutta methods or other approaches. But assuming I can get those derivatives, and I plug them in up there, I can use this idea of you can integrate the linear part exactly, and I can write down this equation which now has this linear combination of phi functions. So I've integrated exactly the linear differential equation AU plus just the time dependent part. So that gives me an expression of that form in the yellow box that I now need to evaluate. So I've got phi 1, phi 2 up to phi p at the argument ta times some different vectors u, where the u's are these derivatives. So the question is, how can you evaluate that expression? So one way to do it would be to develop numerical methods for the exponential. Well, we have those already, in fact, and develop numerical methods for the phi functions and apply them separately to the first part and the last part. And there are some papers on developing methods for the phi functions. But what I wanted to point out that there's another way of doing it, which really goes back to an idea of Sard in 1992. So Sard noted that if you want to compute phi 1 of A times a vector, then you can do it by forming a slightly augmented matrix. So you augment A with B, the vector B, and you just put some zeros at the bottom here to make the whole matrix square. So this is an n plus 1 by n plus 1 matrix now. And if you take the exponential of that matrix, then the required phi 1 of A appears in the top right hand corner. So you can get phi 1 times a vector from the exponential of a slightly larger matrix. Okay, so that was back in 1992, and in fact that idea can be generalized to an arbitrary number of phi terms. So this slightly complicated looking theorem is just generalizing what Sard did quite a bit. So the idea is that now we want to compute this linear combination of phi functions. This is what we had a couple of slides ago in the integration formula. So I want to compute sum of tau k, phi k of tau a times these u vectors. And to do that, I do the analog of what Sard did. I put my u vectors to the right of A. So I augment the matrix with all the columns of u on the right hand side of A. And then in the bottom of the matrix, I've got a 0 block and a j block. So j is 0, I, 0, 0. So the whole matrix is n plus p by n plus p, where there are p of these u's to compute. And then the theorem says that if you compute the exponential of tau times b, then in the top right hand corner, in the last column, you get all these combinations of phi functions. So the very last vector in this exponential matrix, in its first p components, it has all these different combinations of phi functions. And the case j is p is the one that we really need for the integration formula. So the net effect is that you can compute the linear combination of phi functions with a single exponentiation. So you just form the augmented matrix n plus p by n plus p, exponentiate, multiply by this vector, and then if you pick out the first n components, you'll have your u hat. And of course, you don't actually have to form this exponential explicitly. What you really want is this times the vector. So this is really one of those f of a times b problems. Exponential of a matrix times a vector. And so any method you have available for e to the a times b, you can then apply to the to this problem without especially needing methods for the phi functions. There is one little minor problem with this whole approach, which is reminiscent of what I said yesterday about the, remember for the Fresher derivative, we had this method of you form a 2n by 2n block matrix, f of that gives you in the top right hand corner the Fresher derivative, and I said there you have to think about the scaling. Well, here we also have to think about the scaling. We've got a and we've got u, and we've got this matrix j of noughts or ones. So j has a natural scale, the biggest element is 1. If a or u has very small or very big entries, then numerically I could have problems in this evaluation. There is a way to partially alleviate that, because you can stick some scale factors in here to scale a or u, but you just have to be aware that if your problem is badly scaled, you will need to take account of that in evaluating this expression. Okay. So let's go back to where we were, looking at f of a methods. And we've just seen the parlet method fails if you have repeated eigenvalues. And the way around that is to do, well, just simply a block version of Parlet's method. So all you do is think of T as being a block matrix. And the idea is going to be, the problem with the Parlet method is that if you have the same eigenvalue in more than one diagonal entry, it causes a problem. So what we want to do is to block and reorder our matrix so that no two blocks have the same eigenvalue in common. That's the basic idea. So there's some reordering going on and some blocking to achieve this. So if we assume for the moment that the eigenvalues of Tii intersection eigenvalues of Tjj is the empty set, so that no two blocks have got any eigenvalues in common. If we just assume that, and if you write down the equation Ft is Tf, just as we did for the standard parallel method, then exactly the same analysis applies. The F will have the same block structure, importantly. Okay, so F will have the same, this was one of our basic properties. So F has the same block structure, and taking the equation Ft is Tf leads us to these equations here. So the only difference from before is that we have to remember that these blocks don't commute, so we have to keep these terms in the right order. So Fij is the block that I'm going to solve for in this equation, and because these are now matrices, we now have the Sylvester equation. Before we could just divide through by Tii minus Tjj, but now we have what's called a matrix Sylvester equation. I don't know whether you're familiar with Sylvester equations. You know, in general, a general Sylvester equation might be written Ax plus xb is c. It's just a particular form of linear system that occurs commonly in many applications. And in general, this equation has a unique solution precisely when A and minus B have no eigenvalues in common. So in this case, we need Tii and Tjj to have no eigenvalues in common, and that's what we just assumed anyway. So we can solve this equation for Fij, and we can solve it in the same order as before, either a block superdiagonal at a time or a column at a time. On this slide, I've not made the assumption about this. Distinct blocks having no eigenvalue in common here. So the reason I've written singular systems are possible, I've not yet on the slides talked about reordering. So if you didn't reorder and just did this straight off the bat, then there's no guarantee that system is non-singular. So our job is to make sure that the Tii's and Tjj's have no eigenvalues in common. So how do we do that? Well, what we're going to do is do some preliminary transformation. So we get our shear form, and then we do some further computations on T. So we get a T tilde, which is, say, WT W star. And W star is unitary. And the job of the W's is to reorder the matrix T, maintaining triangularity and just shuffling the eigenvalues around along the diagonal. Okay, so T tilde will still be upper triangular. It will have the same diagonal entries but in a different order. And the superdiagonal will have changed completely in general. So how to do that is quite subtle, and I'm not going to say anything about it at all. There are some papers in the 70s by Pete Stewart, by Bai and Demel later on in the 90s, that they describe the method that Ellie Pack uses, but we can disregard that as a black box. So there's an Ellie Pack function, so I can give it the T and I can tell it what order I want it to put the diagonal elements in. So for example, let's just take an example. Suppose that my T comes out as 1 plus I, 1 minus I, 2 and 1, and then some stuff on the off diagonal that I don't really care about. So I've got 3 eigenvalues 1 there, so the standard parallel method is going to fail It's going to divide by 0. So I want to get these 3 eigenvalues together on the diagonal. So I want to reorder this so it's of the form 1, 1, 1, and I might as well keep the other things in the same order. And then something up here. Okay, so now I can block this matrix like that. And I'm going to have a block with the same eigenvalue, but each of the 4 blocks has got different eigenvalues. So I can call the LEPAC routine, and I can say I want the elements in places 1, 3, and 6 to be all together in places 1, 2, 3 along the diagonal. So I just give it this information about the reordering, and it will go away and do a unitary transformation to take this matrix into that one. And it's basically doing Givens rotations to move things around. But it might need quite a lot of Givens rotations if I have things that are far apart that have to be brought together. Okay. But that can be regarded as a black box that will do the reordering for us. So we have to decide what the ordering is, and then that can be done by LEPAC. So that's a particularly clear case where we just have repeated eigenvalues. In practice, we're very likely to have repeated eigenvalues, but what we will have is close eigenvalues. So a more likely scenario would be, and it suffices to look at the diagonal of T, or indeed to look at the eigenvalues. So we really only need to look at the eigenvalues of the matrix A. So suppose the eigenvalues are, let's say it's 1, 1.01, 1.02, 2, 2 plus 10 to the minus 4i, 2 minus 10 to the minus 4i, 10 and 50, for example. Suppose that was the spectrum. Then we basically want to group these eigenvalues into clusters so that all the eigenvalues in the cluster are close together and those in different clusters are far apart. So a natural clustering would be to put the 1, 1.01 and 1.02 in one cluster, to put these 3 eigenvalues that are very close to 2 in a cluster, and then these can be in their own little 1 by 1 cluster. You know, so pictorially, we've got some eigenvalues near to 1, some eigenvalues near to 2, 10 and 50, and we've got these 4 clusters which are nicely separated. So within a cluster, everything's close together. Between the clusters are far apart. So the blocking I would want here would be a 3 by 3 block with these numbers, 3 by 3 block with these numbers, and 2 1 by 1 blocks. What you take as the criterion for clustering is somewhat arbitrary, but what we use in practice is is 0.1. So in the function funm in MATLAB, we say that 2 eigenvalues should go in the same block or the same cluster if they are a distance 0.1 or less apart. So that 0.1 is somewhat arbitrary, but it's a number that seems to work pretty well in practice. It seems to be as good as any other choice of tolerance. So we choose our clustering, normally 0.1, clustering parameter. We then have to determine which clusters we want the eigenvalues to go in. And then there's the practical question of, well, basically letting LEPAC sort out how to do the reordering. Okay, so after we've done all that, we do now have a triangular matrix of the required form. It's got this block form, and the individual blocks have distinct spectra that are within the block. The eigenvalues are close. So we now can look at any one of these blocks and consider the question, how do we compute f of a diagonal block? So how do we do f of TII? So I sometimes call this an atomic block because it can't really be split any further. We've split the blocks as small as we can get them. But the key thing is that this has got close eigenvalues. So if we write this as sigma I plus m, where sigma is the mean of the eigenvalues of the block, and a neat formula for that is the trace of Tii over, well, if the block is, let's say, m by m, would be trace over m. So Tii has got eigenvalues all very close together, so the mean of those eigenvalues, which I'll call sigma, I will put here, so sigma I plus, and this matrix M is going to have some tiny elements on the diagonal. Because these elements are the difference between the mean and the individual eigenvalue, and those are small. Those are certainly less than 0.1. Okay, so if I write things in this form, I get a sigma times I plus a triangular matrix with fairly small diagonal. So one way I can compute f of that matrix is by using a Taylor series. Okay, so I can just say f of Tii is f of sigma I plus m. You know, so this is f of sigma I plus f dash sigma I m dot dot dot. So I can just write down the obvious Taylor series expanding about sigma I, which is the mean of the eigenvalues. And because m has got this special structure with the epsilons on the diagonal, I would hope that this Taylor series will converge quite rapidly. So I would hope the powers of this matrix M will decay rapidly. And that will generally be the case. So here's if you just look at this 2 by 2 case here, epsilon alpha naught minus epsilon, and in fact the trace of M will have to be 0, won't it? So that, yeah, so it has to be epsilon minus epsilon. Here's the 2kth power, here's the 2k plus first power. I mean, obviously the diagonal elements just power down to 0 quickly. The only question is about the off diagonal. So if alpha is 1, say, then clearly the off diagonal elements are also going to 0 quite rapidly. The only problem is if we have a large value of alpha, so say alpha was 10 to the 6, the even powers of m are small, but the odd powers of m will be a bit bigger because of a 10 to the 6 here. So it's going to take a while for these epsilons to get that 10 to the 6 small. So you have to be a bit careful how you truncate the Taylor series because of this phenomenon. So we can't just stop when the next term of the Taylor series is small, because otherwise we'd be stopping at an even power, even though the next odd power is much bigger because of this alpha. So I won't go into the details, I don't think, of how we do that, but we have a way of being careful about when to stop the Taylor series, stop evaluating the Taylor series. Okay, so we've just about got the basics of the algorithm now. We apply this shear reduction, the reordering and blocking, then we apply f to each diagonal block by a Taylor series, and the off diagonal blocks we then get via the block parlet recurrence. Here's just a summary of the key features of this approach. So it can actually be order n to the 4 operations in cost. So how can that happen? Well, it's possible that the block is just one single large block. So if you give this algorithm, for example, a Jordan block, which is already triangular and has got all its eigenvalues equal, you'll just have one huge block. You can't split those eigenvalues. And then you're going to evaluate that by a Taylor series. And well, if it was just a Jordan block, that's okay because that's bidiagonal. But although it's going to fill it, isn't it? So yeah, so the Jordan block, when you evaluate the Taylor series, if you need n terms, it could potentially be of order n to the 4. But this really almost never happens. So in practice, this is an order n cubed algorithm. Although mathematically, we'd have to say it could be n to the 4. We need derivatives, of course. In the Taylor series, we're going to have to evaluate derivatives of f. But then that's not surprising because derivatives appear in the definition of matrix function. And here we're making no assumptions about f or a. This is completely general functions and general matrices. We've got this parameter that we take to be 0.1. We know there are examples where the algorithm fails, and there are examples, we were able to construct an example where no matter what you choose for delta, the algorithm is unstable. Though we've never seen that happen in practice. So this is not an algorithm we can guarantee is, absolutely guarantee is backward stable, but in practice it does perform pretty well. And so I would say this is the best general purpose algorithm for f of a matrix. And so if you're developing an algorithm for a specific f, it's a good idea to compare it with this one and see how it compares. MATLAB's FunM has used this algorithm since 2003. So, and in fact, if you even if you evaluate the log of the matrix function, it actually uses FunM and does something special for the log of the diagonal blocks. So this is a pretty widely used function in MATLAB. Okay, just let me give you one example. Suppose you wanted to use this algorithm to compute the exponential plus the cosine of a matrix. What you should not do is apply the algorithm to exp and then apply the algorithm to cos and add the results together, because that would be wasting a lot of computation. Think of this as just a single function. See, we don't want to compute the shear form twice, we only want to compute it once. So you need to provide the function with the ability to compute f and the derivatives, because your a may require derivatives up to the nth derivative. So here's a little function that will, given x and k, it will return f of x, it will return the kth derivative of f at x. So if k is 0, you're just getting the function value. In general, you're getting a derivative. So this is what's needed by FunM to run. And so if it has blocks of size bigger than 1, it will be invoking derivatives via this call here. But most of FunM is independent of f. It does a shear decomposition, it does a reordering. Those don't depend on f at all. They just depend on the eigenvalues. So the only place where the f dependence comes in is when you're doing f of the diagonal blocks via the Taylor series, and then that invokes these derivatives. So it doesn't matter how complicated that function is, the cost is essentially the same, modulo the cost of these scalar derivatives. So that's one nice feature about this approach. Right, so I'll finish off with a few words on matrix iterations now. And I mentioned the sine function already. So here's just a recap, or a more formal definition if you like. So let's take the Jordan form of a matrix. Let's partition it so that the eigenvalues of the J1 block are in the left half plane, and the J2 block has eigenvalues in the right half plane. And I'm assuming that there are no pure imaginary eigenvalues. The sine function is not defined if we have a pure imaginary eigenvalue. Then the sine function is just, you keep the z the same and you replace J1 by minus the identity, J2 by plus the identity. So what's happening is that we are mapping eigenvalues in the right half plane to +1, and eigenvalues in the left half plane to -1. So if this is an eigenvalue, if this is an eigenvalue, this one gets mapped to +1, this one gets mapped to -1. So any eigenvalue gets mapped to whichever of +1 or -1 is the nearer point. And you throw away the off-diagonal part of the Jordan form. So that's, in a way, the simplest definition of the sine function. Another definition, or an equivalent characterization, is that equation there, which is the most concise way to define the sine function, but a bit more hard to see what's going on. So you square a, and then you take the inverse of the principal square root of a, and multiply by a. So in the scalar case, this would be z over z squared to the half. Okay, and that is going to give you just plus or minus 1. So why is the sine function interesting? Well, I do have lots of examples, but I think I'll not give any because Peter Benner, well, I'm sure next week, say much more about this. But there's applications in eigenvalue computations, lots of applications in control theory. Plus, it's just an interesting function to explore anyway. There's even an integral expression. So that infinite integral is another way of expressing the sine function. So it's a good little exercise to prove that. And if you think back to what I said yesterday, if you want to prove this expression, then it suffices to prove it for diagonalizable A. And that means it suffices to prove it for scalar A. So you just need to evaluate 1 over t squared plus a squared from 0 to infinity, which I think is an arctangent. So that's a neat little exercise to do that and check that you will get sine A. So of the different methods for computing the sine function, the classic method is the Newton iteration. And this comes from applying Newton's method to the equation x squared is I. So why is x squared is I? Well, the sine function is, we just said it's a squared to the minus a half. So if you square that, it's a bit of a mess, but everything commutes. So I can rewrite that as a squared to the minus a half, a squared to the minus a half, which is a squared to the minus 1, which is identity. So that's one way of seeing why the sine squared is I. But it's even more obvious from the Jordan form definition, actually. So if you apply Newton's method to x squared is I claim you get that iteration. I better prove why that is, though. So, can anybody tell me what Newton's method is? What's the formula for Newton's method? For f of x is 0. So in general, if I want to solve f of x is 0 by Newton's method, what iteration do I set up?
So we should apply the differential derivative to the equation. So we write it in the equation form.
Right.
Then we try to find differential derivative. Then the differential derivative times the previous iterate gives the new iterate. The previous iterate minus differential derivative inverse times previous iterate gives the new iterate.
Yeah. So that's Newton's method applied to a matrix equation. Right. So that would be one way to go about it. In this case, there's an even simpler way. Forget all that stuff about differential derivatives. Just think from first principles, what is Newton's method? It's the first order expansion. So I want to solve I is, call it a plus e squared. That's a squared plus ae plus ea plus e squared. And in Newton's method, we drop the higher order terms, so we drop the e squared, and what's left is ae plus ea is I minus a squared. So, I mean, this of course is the Fresher derivative, but I don't even have to think about that. And I just now solve this equation for e. So let me assume that e commutes with a to make things simple. And so e is a half a inverse times I minus a squared, which is a half of a inverse minus a. And so a plus e is a half of a plus A inverse. All right, so it seems a bit like I'm cheating there, and I said let's assume A commutes with E, but the E I've ended up with does commute with A. See, this commutes with A, so everything's okay in the end. So that's the simple way to derive Newton's method for the sine function, which is what we've got at the top there. X naught is A is important because you do need an X naught that is related to A in a special way. So that's the standard Newton iteration for the sine function. And the question is, when does it converge? And there's a nice bit of convergence analysis that we can do. You could reduce this to the scalar case, probably. So if n was 1, this would just be Newton's method for the square root of 1. And we all know how to analyze Newton's method for square roots of scalars. So in a sense, I'm just reducing it to the scalar case here. So the trick is to look at this rational function, g, I minus s, a minus s, a plus s inverse. Because it turns out you can write xk, the kth iterate, as this rational function times s. So s is the sine of a, which is what we're hoping will converge to. So as long as this term tends to the identity, we will get convergence. And what are the eigenvalues of g? So g is a minus s over a plus s inverse. S has eigenvalues sine lambda I. So I've got lambda I minus its sine over lambda I plus its sine. Remember that the definition is sine of lambda I is the nearest point to lambda. So this numerator is strictly less than the denominator. So this quantity is less than 1 in modulus. So the eigenvalues of g are certainly less than 1 in modulus, and therefore the powers of g converge to 0. Standard result in matrix analysis. If all the eigenvalues are in the unit disk, then the powers of your matrix tend to 0. So that means that this tends to 0, this tends to 0, xk tends to s. Okay, and that's the end of the proof. So I think that's the best way to prove convergence of this iteration. Just boil it down to the condition that the result in the purple box there. So it does converge, and the rate of convergence turns out to be quadratic. Not surprising because it is a Newton method. So the error at the k plus first step is bounded by something that tends to a constant times the error squared at the previous step. That is quadratic convergence. Okay, so that's Newton's method for the sine function. Now, in practice, you certainly wouldn't program that as it stands, because convergence can be very slow initially. If you imagine you have a very, very large eigenvalue in your matrix, then on the first step, you're basically saying that the new largest eigenvalue of x1 is a half the largest eigenvalue of A. You're simply halving the eigenvalue. And the same on the next step. So initially, Newton's method for large eigenvalues is simply halving them, which is linear convergence. So it's only once it gets close to convergence that this quadratic convergence sets in. But convergence can be very slow initially. So in practice, you would want to include some scaling in the iteration to speed things up. And one of the exercises on the sheet is to experiment with several different scaling factors for this iteration. So on the example sheet, there are a number of computational exercises that would be great to try out in MATLAB. So I'm hoping that people will have the time to do that. There are also some open problems as well, which if you can solve, you definitely have a paper. So I'm hoping that somebody will solve an open problem as well during the course of the summer school. And I should say that although I'm only here this week, Li Jing is here for both weeks. So I hope you'll feel free to carry on working on those open problems or whatever next week as well. I'm also contactable by email. So things don't just end this week. Feel free to carry on, and there'll be help available. So that's Newton for the sine. Here's Newton for the square root. Now this is a bit more Well, I've written this down in a more formal way. So what I've written down here is, well, I guess it's analogous to this here, isn't it? So where I had AE plus EA is I minus A squared, this is the corresponding equation when it's the matrix square root. So I want to compute the square root of A now. And so in principle, this is Newton's method. You solve this Sylvester equation for EK, and then you update, as shown there. Now, if we had to do that, this would be terribly expensive, because solving a Sylvester equation requires a shear decomposition. It's very expensive. And we've just seen that if you compute a shear decomposition, then the Bjork-Hamling method will get the square root in just one further step by those simple recurrences. So we don't want to be computing shear decompositions. But it turns out that if A commutes with x0, which it clearly will if x0 is A, or the identity, then that reduces to this iteration here, which is analogous to the one for the sine function. So under this condition, xk and ek commute, and so everything simplifies to what's in the yellow box. Okay, so this is the same as the sine iteration, except that we now have the matrix A inside the iteration formula. If I were to delete the A, I would have the sine iteration. And that makes sense because the sine iteration is computing the square root of the identity. So if I put A as I get the sine iteration. So what can we say about the convergence and other properties of this iteration? Well, of course, Newton's method in general, from the standard Newton theory for arbitrary nonlinear functions, we're going to get quadratic convergence as long as we have a non-singular Jacobian at the solution. And this corresponds to saying, essentially, we're computing a primary square root. But which square root does it converge to? It's not immediately obvious. In general, there are at least 2 to the n square roots, because every eigenvalue can go to the plus or minus square root. An interesting fact is that this iteration can converge even when the full Newton iteration at the top breaks down. So they're not fully equivalent. Another observation that's relevant is there's a bit of a lack of symmetry in this equation. So why have I got xk inverse A rather than A times xk inverse? Well, I guess the answer theoretically is that xk and A commute, so it doesn't actually matter which order they appear in. But numerically, it will matter, because there'll be rounding errors, and those rounding errors will propagate through the iteration, and we may get different behavior depending on which side we put the A on. So there's some interesting issues in that formula. And in fact, so I'm just going to jump ahead a few slides now. That Newton iteration is numerically unstable in general. And this was noted long ago by Larsonen in a 1958 paper. So he said, Newton's method, if carried out indefinitely, is not stable when the ratio of the largest to smallest eigenvalue of A exceeds the value 9. So when I was working on my PhD, I was interested in these sorts of iterations, and I somehow came across the paper by Larsonen. And I read that, and I thought, that's rather odd. Why 9? And what's the justification for that statement? Because I don't think he gave any proof of this. He just stated that. He must have just tried it out, and if the ratio was bigger than 9, he found it was unstable. Less than 9, he found it was stable. So that was a bit of a puzzle when I was working on my PhD. There was also a paper I found by David Blackwell. He's a famous statistician from Berkeley. I think he died just recently. He, in a paper, describes this same Newton iteration, and well, basically he discovered it himself when playing around with matrices, and thought this was really fun. And he wrote a couple of pages about this in a sort of expository paper. But he wasn't aware of any of the background to the problem. So in my thesis, I did some analysis of this iteration, and I was able to explain the instability, and I was able to show why the value 9 arises. And I did it in a somewhat ad hoc way by just sort of tracking the way that errors propagate in the iteration. So I assumed that A was diagonalizable, so I can now, without lots of generality, think of A as being a diagonal matrix. And then I did some error analysis and basically looked at how the errors propagate at an element-wise level. So I was able to come up with some explanation of Larson's result. But what I did was very specific to this particular iteration. And I would have had to start and do the analysis again if I was looking at a different iteration. So what I'll explain tomorrow is a way of analysing this instability that's more general and would apply to really any iteration of this form. And it's something that I've only really come up with in starting about 10 years ago in a paper with a couple of colleagues. We had an idea of how to do this more generally, and that was then refined for my book on matrix functions. So we'll talk about that tomorrow. And we'll also talk about the convergence of the matrix square root iteration. And then we'll carry on to look at methods for f of a times a vector, which is the particular problem that arises in the exponential integrator application. And I'm also at some point tomorrow or Friday going to talk about software and available software for matrix functions. Okay, but I think that's probably a good place to stop, and we'll take our 20-minute break.